Got it? All right. Let's begin with a word of prayer. All right? I'll start. Ahem. 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 Dear Heavenly Father, we thank you for this day. I thank you for these students. Just pray that you just bless our work today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So guys, do you have any questions about the homework? So everyone understands all of the homework? That's good. Yep. Number 6. I got it. I'm actually prepared this time. I'm assuming we're talking about homework number 2, right? Okay, good. So we're supposed to find the limit if it exists. And so the limit we're asked to calculate, at least in my version, yours might have a slightly different number, but if I solve this one, you'll be able to solve yours, I'm sure. 2x squared minus 9x over x. Right? Something like that? Okay. So first thing we do is we try to plug in the limiting value. What happens when you do that? Try to put in x equal to 0. What do you get? 0 on the top, 0 on the bottom. This thing has type. It has type 0 over 0. It's indeterminate, right? So how do we fix that? Algebra, right? You say factor out an x. I think that's a good move. So we can factor x out of the numerator. That's x times what? X times 2x minus 9 divided by x. Right? And then what can we do? Cancel the x's. So we have the limit as x goes to 0 of, yes, bless you, 2x minus 9. Aha, now we go back to our original attempt, just try to plug in the number. Can we do it now? Plug in 0, what do you get? 2 times 0 minus 9. Again, this is a shorthand for using those limit laws, but so for my example, it's minus 9. Does that help? Of course, there's another way you could have done it. You're like, one way is enough. I know. But this is also simplified as 2x squared over x minus 9x over x, right? Which then is 2x minus 9. So if you look at the algebra, this is another way you could have done the algebra to get to the same 2x minus 9 ultimately. But the factoring out's a good idea, like I did in the blue. So is there another question, or any have more questions about this? Yep.
Can we do more, not more complicated, but just more practice in the IBT that was the last question of the homework?
Sure. Indeed. Let's see here. In fact, I'll work my last problem in the homework, which is probably slightly different than yours. This was number 6, was it? What I'm about to do is tell you what, let me do it over here. Number 9. No, it's number 15, right? So we're supposed to use the intermediate value theorem, or the IVT, to find constant c such that f of c is equal to m. In particular, in my problem, I'm given f of x is equal to x squared minus x plus 1, and that's on the closed interval from 0 to 9. And I'm also given that the value for m we're looking for is 43. Okay, so how do we do this problem? When does the intermediate value theorem apply? First of all, 0 to 9 is a closed interval, right? That's good. We need a closed interval. That's part of the ingredients. It's a closed interval. I didn't even emphasize that last time, but that's part of it. The function, is it continuous? Yeah, it's a quadratic, so it's certainly continuous. It's continuous. It's got no jumps, right? It's continuous on this closed interval, 0 to 9. So the intermediate value theorem says if you look at f of 0 and if you look at f of 9, then any value between those, whatever those two things happen to be, this function has to attain those values at least once. So let's figure out f of 0 and f of 9 and make it less abstract. What's f of 0? 1, okay. F of 9 is what? 9 squared minus 9 plus 1, otherwise known as 81 minus 9 plus 1. What is that, 73? So the intermediate value theorem tells me that any number between 1 and 73, right, you give me any value between 1 and 73, there's some c between 0 and 1 such that f of c is equal to that value. The value that the WebAssign has given us is 43, right? So the intermediate value theorem implies that there is some c which is in the interval 0 to 9 such that f of c is equal to 43, because 43 again is between 1 and 73. It's an intermediate value. Right. Now the intermediate value theorem doesn't tell you how to find it, but it tells you it's there. How do we find it? Yep. Right. So, or if you were so inclined, you could even use c as the variable, but we'll use x since x always goes better. If I do algebra in the letter c, for some reason it's like harder to understand. Let's see here. For many of us, plus 1 is equal to 43. So I need to solve this. I'm also looking for a solution that's in the relevant interval, right? I'm looking for some solution between what? Between 0 and 9. How do you solve this? Minus 42 is equal to 0. Let's see, how do you get 42? How about 6 times 7? 6 times 7 seems like a good choice because 6 minus 7 is minus 1. So yeah, that factors to x minus 7 times x plus 6, I believe. So from that, I can read zeros, right? That gives me two solutions. I get x equals to 7 as a solution, and I also get x equals to minus 6 as a solution. Oh,
Can negative 6 even be an answer because it has to be in between 0 and 9?
Well, that's the thing, is we have to pick the one of the solutions which is relevant. When I solve the equation equals to 43, when I solve f of x equals to 43, the algebra doesn't know that that's done with respect to the closed interval. The algebra is just going to tell you everywhere that the polynomial hits the number 43. In particular, it hits it at minus 6, which we don't care about, right? So the solution that we're looking for, essentially by common sense, is this one. So there you go. So therefore, c is equal to 7 for my problem. Now, the details of yours may be a little different, but it's basically that. Does that make sense? Or? Yep.
So let's say it was 7 and it was 6. Would it then 43 deal with intervals equal 43 in both places, which is both the solution? Or what would you use as your option to correct?
Oh, Okay, so you're asking, what if we had a different problem, right?
Yeah, what she called it.
So, yeah, let's say number 15 tilde. Let's say that you had looked at, instead of 0, let's replace 0, 9 with, say, goodness gracious, I don't know, how about minus 8 to 8 or something like that, yeah. Or what you said would also be fine. If I did that, right, if I did this as my interval, then I would check, I would have f of minus 8 was something, I would have f of 8 is something. What would those be? So f of minus 8 is 64, minus of minus 8 is 72, 72 plus 1 is 73. F of 8 is 64. What? Huh.
64, 56, 57.
What is it?
I think it's 57.
You think it's 57? Okay. And what's this?
Wait, no, you would be right. It would be 72 because it was negative 8, and then it was, so it was 57 for f of 8.
Uh-huh.
Yeah, I did apologize.
And what's this one?
Yeah, that's 57.
57, okay. Oh no, the theorem doesn't work. What's going on? Look, is 43 between those values? No. The theorem doesn't really speak to 43 here. All this theorem says is that if you have a value between, in this case, in our new example, 57 and 73, there's some value between minus 8 and 8, which we can put into the function and get back 43. I mean, get back that value between 57 and 73. It's really easy to understand what's happening geometrically. What's going on here, right, if you look at it. And so it's not really that surprising once you think about what's going on geometrically here. But we've got this, quadratic x squared minus x plus 1. What does that look like? Let me remind you that that's, it's x minus 1/2 quantity squared. And then if I complete the square, which I just did here, right? X minus 1/2 quantity squared, that means I added a fourth. I have to subtract a fourth to be fair. So you have plus 3/4. In other words, by this little bit of algebra, I can see that the vertex of the parabola is at 1/2, 3/4. So, and what is the value? Well, at 3/4, right? So vertex of this thing it's kind of close to the origin in our picture. And then it does not seem right. Anyway, let me not distract myself. So apparently 1/2 makes a big difference. It's not quite on the center line, these two numbers. So it's something like that, right? So it's bigger over here. Here is minus 8, 73, and this point here would be 8, 57. So where's 43 in this picture? It's like down here, right? So, what was it? Oh, you're good? Okay. So basically, between the values 57 and 73, right? Yeah, I mean, the graph hits it over here, right? But the graph also hits values below those, right? Because it dips down and comes back up. So the intermediate value theorem doesn't tell you that this doesn't happen. All the intermediate value theorem tells me is that it does absolutely hit values between 57 and 73. In fact, you can see that they're going to be attained like over here. So if if we had picked a better endpoint for your modified problem, you would have also picked up minus 6 as an answer. I mean, there doesn't have to be one C.
Okay.
There can be many C's. Right? And just because the value is not between f of a and f of b, it doesn't mean that the function doesn't hit it somewhere either, as we see from this example. So, to be careful not to like overextend what the theorem says. So, here, let me give an easier example just graphically. Let's free ourselves of the formulas and just like look at this function. You can have a function that looks like this, right? And if you pick, this is a and this is b, so here would be f of a and here would be f of b. So here's f of b equals y. Here's f of a equals to y. So, there's these little, it's not, the function can escape this band. It can go above and below f of b and f of a. The intermediate value theorem doesn't have anything to say about that. What the intermediate value theorem says is if I draw some horizontal line between f of a and f of b, right? If I draw any intermediate value like this, and that's what we've been calling m, or we called m in the problem there, then there has to be at least one point it hits. But there doesn't have to be just one. There could be a bunch of them. For a quadratic, there'll be at most 2. But that's the nature of a quadratic. Anyway, for your problem, there's just one. So, and the other one's an extraneous solution. Yep.
For testing and everything, would we have to go from like x squared minus x plus 1 to find the vertex of that, or are we allowed to use our calculator? Would we have to go very specific to explain how we got a certain answer?
I mean, there may be a problem where you'd want to find the vertex of a parabola. I mean, that's, yeah, it could happen. Probably not, but yeah. We will soon learn techniques of calculus which will allow you to find the vertex whether or not you understand completing the square. It's kind of neat, but yeah.
I'll take this over a problem like 8.
Like 8? Sure. I know it's always dangerous to bring up completing the square. It's a sore spot with some of you. You have bad memories of previous classes. Being forced to go through this seemingly meaningless system of steps, which doesn't really make any sense because I have the quadratic formula, so why not just use that? I get it. I understand. I was you once. For me, appreciating the completing square idea only really gelled for me personally in differential equations. And at that point, all of a sudden, it just became like, oh, well, this isn't hard. That may or may not have happened for you yet. It might not ever happen for you. And it's probably not a big deal in here. Okay, so which one was it you said? 8. Like 8? Something like 8. Use the graph of the function to find the limits at the indicated value of a if the limit exists. So we were asked to do something like limit as x goes to a with a minus on it of f of x, right? Limit as x goes to a with a plus on it of f of x, right? Limit as x goes to a of f of x, just plain, right? So equals, 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 fill in the blank, fill in the blank, fill in the blank. And we need some graph, right? So let's see here. For me, I don't know if you guys have different graphs. Here I'll do a equals to 3, but I'm going to mix it up a little bit. I'm going to do a different graph than the one that's in here, because I think you guys have the same graph as me. I don't want to just solve the problem that will rob you of the chance of learning what you need to learn here. So, I don't know, the function could look like whatever. All right, so here's your y equals f of x. And this is supposed to be at, let's say, 4. And let me suppose this one's at like minus 3. All right? So the limit as x approaches a with the upper minus is also read as x approaches a from the left. So what you're going to do is you're going to look at values of the function a little bit less than a. In this case, a is equal to 3, right? So to understand the value of the top one, what do? We think about points getting closer and closer and closer and closer and closer, 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 like that, right? And so what are they tending to? They're going to what value? Negative 3. So we put a minus 3 here. The left limit is minus 3. Now, this little plus means that you're looking at a right limit. You're approaching the limit point from the right side. So over there, you're going and you get closer, 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 closer. See what you're tending to. What are you tending to? You're tending to 4. So the right limit is 4. How about the double-sided limit? It does not exist, right? The only way the double-sided limit can exist is if both the left and right limits both separately exist and are equal. So we simply write does not exist here, which is probably DNE. I don't know. It will tell you in the problem the formatting for that. Yes, sir.
What if one of those wasn't
I think it's capital DNE is what my key has.
What if one of those wasn't a circle?
Doesn't matter.
They were both dotted and they were the same.
They could both be circles. They can't both be dots. That's not a function. If they're both dots, that means the value of the function at 3 is both minus 3 and 4, and so the function would be double valued, which means it wouldn't be a function. Right?
It would be two separate things.
So
Yeah.
will it never exist? And it approaches both?
Yeah, if the function has a jump in the graph, that means that the right and left limits don't exist. I mean, don't separately match. If they don't separately match, that means the two-sided limit doesn't exist, which incidentally means the function's discontinuous at that point. This is called a jump discontinuity. Remember what was a continuous function? If f is continuous a, what do we have? We have the limit as x goes to a of f of x is equal to f of a. That means that's our definition for f continuous at a, right? So this function is not continuous at 3. It's not too badly behaved either, though, right? The left and the right limits exist and are finite. So later we could integrate the area under this function without much trouble. It's not bad. If we had vertical asymptotes, that'd be worse. Other questions? Okay, I'm going to get into the next section then, which of course is on derivatives. Don't clap yet. We're still doing limits. So today I'm going to talk to you about the definition of the derivative. The definition of the derivative we state in terms of limits. That's why we've been doing limits, so that we can understand the derivative. So let's talk about derivatives. Well, I'm going to start with I'm talking about the derivative at a point. So let's see here. Here's a picture we can draw. So here's the point in question, A, right? Then I think about another point on the graph at, say, a plus h. All right, this curve I drew is y equals f of x. So we're given some function, and what we want to do is we want to find a description of the slope of the tangent line. All right. So the tangent line, I'll try to illustrate in green as best as I can. It's this thing. It's a tangent line, assuming that it exists. You could come up with functions which don't have tangent lines at certain points, like if there's a kink or a corner in the graph. Now, so what you do is you imagine secant lines, like this one. This is a secant line. Secant line, all a secant line is it's just it's a line between 2 points on the graph. That's all. It's not complicated, right? You give me a graph, give me 2 points, connect the dots, that's a secant line. But we're looking at a family of secant lines where one of the points on the secant line is fixed. It's this point of tangency. What is the point of tangency? Yeah, that point is a comma f of a, right? The y-coordinate's f of a. And so what's the slope of the secant line? Let me draw a little red triangle here. So what's the so-called the run, the x? How far does it go in the x? A plus h minus a, which just gives you h, right? And how about this one? That's f of, see this point up here is what? That would be f of a plus h is the y value there, right? And then I have to subtract f of a. So you could use this notation. You could say, okay, well, this is the so-called change in y, and this is the change in x. Triangle is just shorthand for change. So the change in y over the change in x is equal to f of a plus h minus f of a, all divided by h. This is a so-called average rate of change. So the average rate of change is identified with the slope of a secant line. And it's by no means a unique thing. Like if you give me different values of h for a particular fixed choice of a, you get different averages. I'll work this out with numbers in the next example in just a second, all right? But the average rate of change is by no means unique. On the flip side, because I could draw other red lines which would connect 2 points. I don't want to do it, it'll clutter my picture. But the tangent line it's unique, right? And the way to get the tangent line, the slope of the tangent line in particular, what I want to talk about, is this. So the notation is f prime of a, which is, by the way, the slope of the tangent line. And I say the tangent line. This is just a secant line. There's lots of other ones. So the tangent line, it's just equal to the limit as h goes to 0 of this difference quotient. The difference quotient is what I just wrote for the average rate of change. So f of a plus h minus f of a, all divided by h. So there you go. That's the definition of the derivative at the point A. I'll put a box around it. It's important. You need to know this. When I ask you to calculate the derivative from the definition on the test, you have to work through this. All right? I know some of you still remember nice shortcut formulas that you learned in high school calculus, and that's great. And we'll get back to those shortcut formulas, but we have to understand the definition before we do that. Any questions about this? This is how your book has it presented. There's another way to write this, and I'll show you that after I do an example. Okay? Let's do an example. Let's find the derivative of f of x equals to x squared plus 3 at a equals to, let's do 2. Okay? So what does that involve at the moment? We have to say what's f of 2 plus h is equal to what? What does that mean? We plug in 2 plus h for x, we square that, and then we add 3, right? That's why it's important for you to understand the composition of functions. We're composing f with the function 2 plus h. Now you FOIL this out, what do you get? You get yourself a 4 plus 4h plus h squared plus 3. But, of course, we also can calculate what's f of 2. Two squared plus 3, right? Which is what? Yeah, 7. Now, we could have cleaned this up too, right? What is this? This is actually what? 4h plus h squared plus 7, right? Now I'm doing these parts separately so that you can understand what I do next easily. So I'm going to call this thing 1. I'm going to call this thing right here 2. Okay, so we can use 1 and 2 in what follows. So what happens here? I'm going to look at the limit as h goes to 0 of f of a plus h minus f of a. Oh, let me be more specific. What's a equals to? 2. All right, so 2 divided by h, right? So let me write it out. What is that? That's the limit as h goes to 0 of by 1, 4h plus h squared plus 7 minus what? F of 2 was 7, right? All divided by h. If you'll allow me this manga style comment, this is f prime of 2. The manga is read this way. None of you read anime? You don't read anime, right? But anyway. You know, like the manga, you read this way. I'm sorry, is it manga? I don't know. I'm not Japanese. So 7's cancel, right? What are we left with? Yeah, we get 4h. So we can factor an h out, right? This is h times 4 plus h divided by h. The h's reduce, right? Cancel out multiplicatively. What are you left with? Just 4 plus h. What's the limit? Exactly. So the answer is 4. The slope of the tangent line here is 4. What's the equation of the tangent line? The equation didn't know it's not 4. The equation of the tangent line, what would that be? So we could do y is equal to f of a plus f prime of a times x minus a. That formula is something you can go back to and use to find the tangent line. That formula puts the y value at f of a when the x value is a. And that formula gives you the equation for a line that has slope f prime of a, right? In other words, that is the equation of the tangent line. And then all you got to do is just put in the details of our problem. What are the details of our problem? We have f of a is what? F of 2 is 7. So y is equal to 7 plus what? Plus 4 times x minus 2. And that, folks, would be the equation of the tangent line for this example. I can even be so foolish as to try to graph the whole thing to show you what's going on. This one's not too hard to graph. X squared plus 3 is a parabola. It's got a vertex, which is the y-intercept at 3. And we just found the slope at, we found the tangent line like here has slope 4, and it looks something like, that doesn't have to go through the origin. Where does it go? I don't know.
Can we simplify even more?
Yeah, sure. So that's 7 plus 4x minus 8. So apparently that's 4x minus 1, right? So if I had drawn this better, here, let me fix it.
So, but either one is acceptable.
Oh yeah, well, it depends on the question, but if the question asked you to leave the answer for the tangent line in point slope form, my original answer would have been fine. If it asked for you to give the answer to the tangent line in the slope, in the, what's it called, the slope intercept form, then what's in red would be the answer. I think that they're the same answer, so on a test I would count either as correct. To me, that's just different ways of, just, are you Matthew, are you Matt? I mean, to me, you are. They're both just different ways of describing a line. Yep.
Okay. So how did you get like 7 and 4 up there?
7 is f of 2. So the point of the point of tangency is that point. It's 2 comma 7, which is f of 2 comma, it's 2 comma f of 2. The point of tangency. Now there's a more basic question to ask: why 2? Because we made it up. That was the given to us in the problem. Yes, sir.
Is that a formula that you put over there, like under the tangent line?
Yeah. This is, you could take this to be the definition if you'd like. Definition of a tangent line is that right there. There's a definition for you. The equation of the tangent line is given as such. Geometrically, that's exactly the same as my picture over here. Yeah.
Will we have to memorize equations for the test, or will we have them?
You have to memorize the definition of the derivative, the definition of the tangent line. Yes, these things you should know.
What did you do up there in the upper left?
The upper left, which upper left?
Upper left.
This?
Yeah.
I'm just calculating the pieces before I use them. Here, let me do another example. I'm just calculating this and this separately before I put it here. I'm just breaking it up into pieces so it's more digestible. Now, this is the, this is the tangent, the derivative at a point. We also talk about the derivative function. What would the derivative function be? The function f, the function, let's say here, if, now this marker's no good. If f, let's see here. I'm not sure how to package it for you guys. Yeah, let me not be too technical. So the derivative function, what's the derivative function? Is simply, it's the mapping A maps to f prime of A. So basically the derivative function at each point is defined to be the value of the derivative at that point. I mean, it's really, let me show you an example. I'm going to, almost the same one I just gave you. So we had f of x equals to, what was it? X squared plus 3. So to calculate the derivative function, I just need to do this basically, I mean, if you want to, you could put a here. Sometimes you put x. I'll put an x here. That might make it more easier to understand for you guys. So if I calculate f prime of x, what would that be? So I'm supposed to do f of x plus h minus f of x. So basically, instead of putting a, I put x, and think of x as being a variable. So the derivative function basically just made from piecing together the derivatives at a point, stringing them together to make a new function. Let's work this out, then it'll make more sense to you guys. Let's see, your limit as h goes to 0 of what? X plus h quantity squared plus 3, right? Minus what? Minus x squared plus 3. Now I got to put some parentheses around what I just wrote. Why? Why can't I just leave it like that? The minus f of x, that minus applies to the whole formula for f of x, right? If I don't put parentheses here, or if I don't at least distribute the minus, I'm going to get into trouble. I'm going to put parentheses, though, because that's a good habit to get into in this step. Otherwise, the most common mistake people make is to not distribute the minus over to the 3. Okay? So we FOIL out the x plus h squared. How's that go? X squared plus 2xh plus h squared plus 3. Now I'll distribute the minus. Minus x squared minus 3, all divided by h. So the 3's cancel, right? Anything else cancel? X squareds, yep. So dead, dying. What survives? Right. And I'm going to go ahead and factor out an h in the numerator. So h times 2x minus, or plus h rather, divided by h. Well, isn't that convenient? The h's cancel again. This happens in every one of these problems once you do the algebra right. There should always be this kind of h cancellation at some point. And what are we left with? We're left with a limit as h goes to 0 of 2x plus h. Which is what?
2x.
Yeah, it's just 2x. X has no h dependence, so h goes to 0. So yeah, we just get 2x. In other words, I have f prime of x is equal to 2x. So the derivative function corresponding to the given f of x here is 2x. So the function was a parabola. The derivative function, right, is a line. Okay. The derivative function is not the tangent line, right? The value of the derivative function at each point gives you the tangent line's slope at that point. For example, what happens when we go back over to here, look at this. So f prime of 2 is what? 2 times 2, which is 4. So why did we work it out with 2 first rather than not just working it out with x? Because it's easier for you guys to follow 2 than x. That's why. Nothing profound. It's just we work with numbers to start with, and then gradually we'll transition to working with variables. Any questions about this? Yep.
How did you go from f with parenthesis x plus h parenthesis to parenthesis x plus h parenthesis squared?
From here to here?
Yeah.
That's what it means, f of x plus h. Well, f of x is x squared plus 3, so I have to replace x with x plus h wherever it is. That's what it means, f of x plus h. I put x plus h in the place of x.
And then the 3 goes away.
Right? So, I mean, more specifically, this guy is exactly these terms. And what's in red is the f of x. Yeah? Okay. Your book doesn't have this, and it's odd to me that they don't, because the other way we talk about derivatives, and sometimes it's easier working out the formula, but another way you can say is you can say f prime of a is equal to the limit as x goes to a of f of x minus f of a over x minus a. Some of you may remember this from high school. I don't know. So this is the alternative definition of the derivative, like this. And so that's basically based on this picture. Right? So if you look at the little triangle here, you've got x minus a, and this is f of x minus f of a. So instead of letting h go to 0, you can let x go to a. It's another way to capture the same behavior. So, potato. I don't know. Some examples are easier to work with the other formalism. So I thought I'd share it with you, even though it's not in the book. Okay? Let's look at an example. I'll let you guys choose. Do you want me to do it with the h or with the thing I just told you over there? With the h? All right. We don't always have to think about what's on the test. That's so boring. Let's see here, x plus 2. How would you do this? 1 over x plus 2. Let's find the derivative. Let's find f prime of a. So I need to do what? F prime of a. You guys have told me to use h, so I'll behave. H goes to 0 of what? F of a plus h minus f of a over h. That's my guideline. That's my template. That's my starting point. What is f of a plus h, though? One over what? A plus h plus 2, right? And then minus what? Minus 1 over a plus 2. That's f of a. What did we do with...
Yeah, I don't get that. It's f of a on the upper left instead of f of x, right? That's not supposed to be f of x. Next to the example.
That's my definition of the function. I mean, I could put Pac-Man here. It wouldn't change anything. No Pac... Oh, I'm sorry. Here, I'll make it better. SpongeBob. Although I've been criticized, my SpongeBob doesn't have enough holes. To the limit of my artistry, that's SpongeBob. So, okay, so this guy, listen, I mean, I could take, and I could put x, 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 x everywhere here. The reason I'm not is because you guys need to think about you need to be able to switch a and x. Like, that's got to be something you get over. Otherwise there's like this unnatural obstacle for you, just in terms of like a notational, yeah. Anyway, let me factor the 1 over h out here. so we don't have to write such a big denominator. So I'm just rewriting this as this whole thing as 1 over h times that fraction on top, okay? How do we simplify that? I'm just rewriting it since otherwise I'm going to lose some of you guys. What's next?
Take out an A.
Common denominator.
Multiply by each other other side.
So you would add an h to the right side.
You know what you want to do. You don't know how to put in the words. I have that feeling all the time. A plus 2 minus parentheses a plus h plus 2. All divided by a plus h plus 2 times a plus 2. So what I did in the purple is just to make a common denominator by multiplying, by cross-multiplying, as you guys like to call it.
No, I get that.
It's like 1/5 minus 1/7 is equal to 7 minus 5 over 35.
I get it.
It's the same thing. Now what happens though? What's the magic of that algebra? We learned this before as we studied limits, that will make stuff cancel out and it makes the limit. See, the form it had before was 0 over 0 actually if you look at it. So what happens here? The 2's cancel, right? What else cancels? The A cancels. And you're left with h over h, which is giving you what? Limit as h goes to 0 of 1, but there's a minus, right? Right, so we canceled out the a with the minus a, the 2 with the minus 2, and then we reduced h over h to give us 1. You guys with me? At this point, we've removed, it's not type 0 over 0 anymore. We could actually plug in the limit. We could plug in 0 and get something, get a value, right? What is the value? A plus 2 times a plus 2, right? So it's a plus 2 squared. Because I get a plus 2 times a plus 2. So now, I hope I'm not going to blow your mind when I write this. Hold on. Like, put your hands right here like this. Hold tight. But f prime of x is equal to minus 1 over x plus 2 quantity squared. Mm-hmm. Right. Now, so the question is, there's two questions basically to ask you guys. The one is to find the derivative at a point. Right? Now, if I say find the derivative at an arbitrary point, that's essentially the same thing as saying find the derivative function, because the derivative function assigns the point, the tangent line, the slope of the tangent line at the point to each point, like for arbitrary points in the domain. Yes? Oh, yeah, sure. So this ends up, the thing I didn't write was h over h.
Yeah.
So those reduce. Because, you know,
And then the h turns into a 0.
it doesn't, it turns into a 1. It's a multiplicative cancellation.
No, the a plus h plus 2, how does that?
I'm sorry. That's just a plus 0 plus 2 times a plus 2, but the 0 adds to just give us minus 1 over a plus 2 times a plus 2, which, by the way, is minus 1 over a plus 2 quantity squared, right?
So we would use this process to use the derivative equation, but we would use the previous time we did to get a specific.
I think they're really the same thing, honestly, but it's a question of interpretation. If the point A is fixed, we're talking about the derivative, the tangent line at a point. If a is allowed to vary, what you're calculating is the derivative function. Yeah, which is what we just did.
So if we were to leave it in the form where a plus 2 squared is x plus 2 squared, we would get it wrong, correct? You asked for x and that's wrong.
I'd probably give you credit still. I think it's, like I said, on the basis of my comment up here, if a is arbitrary, in my book, saying f prime of a is equal to minus 1 over a plus 2 squared is also a description of a function. That said, most of the audience here recognizes it as a function once I put an x there, because you have some sort of psychological attachment to this letter x, meaning something about a function, right? But that is an artifact of your current education. It's not a necessary logical thing. I'll shut up. Yes? No?
Are you finding the tangent line after that?
I haven't found the tangent line yet, but we could
Could we?
pick almost any point.
2.
You're like, I'll pick minus 2. No, that is the one point that's not allowed. Minus 2 you can't do. Minus 2 we got to asymptote, right, in the original function too. So you want to find the tangent line where?
4.
Find the tangent line at x equals to 4. Okay. So it's going to be y is equal to f of 4 plus f prime of 4 times x minus 4 by the definition of the tangent line. So I just got to plug in 4 into the formula for f. To take that SpongeBob and make it a 4, 1 over 4 plus 2. I'm going to write out the steps if it's okay. Just because I feel like I'm doing more than, I don't know, 4 plus 2 quantity squared times x minus 4. Of course, this simplifies to, as you said, 1/6 minus 1 over 36 times x minus 4. So there you go. That is the equation of the tangent line right there. Some of you feel like you're not done unless we multiply that out and rewrite it as mx plus b. That is an unnecessary extra algebraic step that you do not need to take unless you really want to. I like this. To me, this format of the tangent line equation is even better than y equals mx plus b, because I can tell you from looking at this that the point of tangency is what? What is the point of tangency? You can see it from this equation. Look at it. What is it? It's just like, you got to just do matching. The point of tangency is a comma f of a, right? This is the f of a. This is the a. So when I look at this, I can tell you the point of tangency is 4 1/6. I mean, I can just look at that and tell you that that tangent line equation goes paired with the point of tangency being 4 comma 1/6. Now, I knew the point of tangency was 4 because you guys just asked me it. But imagine yourself in a world where you hadn't asked that and somebody just gave you the equation of the tangent line. You can look at it and tell me the slope and the point if it's in this format, like here, hypothetical. So suppose somebody told you, hey, you got a function and its tangent line is 10 plus 3 times x minus 2. Can you, if this is in that format, where's the tangent? Where's the point of the tangent point? It's at 2 comma 10, and the slope of the tangent line is what? 3. So that would be f prime of 3. Yeah. For a function which I did not write, but anyway, I'm getting off track. Yes, other questions? Yeah. No? Oh, okay.
Well, not having to do with this. Have you ever seen the show Numbers?
Not really. I don't know. No, I know. I know I should watch it, but I really haven't. All right. Let's see here. Let us work some more examples. Oh, so I should give you actually more about the instant. So the tangent line also can be interpreted, the slope of the tangent line also has the interpretation of being the instantaneous rate of change of y with respect to x, right? And in the context that y is position and x is time, the average rate of change becomes average velocity, and the instantaneous rate of change just becomes regular velocity, right? So